Now, the second chunk of our structure is the bridge. This is called the ethyl bridge. So by default, our hydroxyl in the carbon 1 or the beta carbon is necessary to have an adrenergic activity. So if you can see, carbon 1 is considered to be chiral center. So it can have a configuration of rectus or sinistro, or the RNS configuration. So it is favorable that the drug contains R configuration to produce maximum activity. But many drugs in the market are sold as racemic in nature, meaning there is both configurations of R and S structures in the drug dosage form. One exemption is our dobutamine. Now, R2 is the second area where we can have modifications or substitution. So, if our R2 is substituted with methyl, it will have adrenergic activity. But if our methyl is changed into ethyl, meaning there is increased number of carbon chain, it is the same with the previous modifications in the first chunk, that increase in number of carbon chain in our area for substitution favors our beta receptor selectivity. So again, R2 or the second R for substitution on our carbon 2 or the carbon 2 position, but it is alpha to our amine. So if we will substitute it with methyl, it will have adrenergic activity, but it has slow metabolism with our monoamine oxidase. If it has slow metabolism with our monoamine oxidase, it can have better oral effectiveness because it can have longer duration of action in our body. Now, for non-catechol compounds or synthetic compounds that are used as adrenergic agonists, it is favorable, or our manufacturers add small alkyl group in our R2 in order to mimic the natural body or the catecholamines, which has methyl or ethyl in their R2, so that they can have increased resistance against metabolism, and also they will have an improved lipophilicity. So separation of our aromatic ring and amino group, it has to be separated with two carbon atoms. Between our aromatic ring and the amino group, there should only be two carbon atoms in this figure here. So that will promote maximum adrenergic agonism. Now, in terms of hydroxyl on our beta carbon, if our structure lacks this hydroxyl, for example, our dopamine, it will have a greatly reduced adrenergic receptor activity. So some of the activity will be retained, but if there is removal of hydroxyl in our beta carbon or in carbon 1, there will be an effect on the adrenergic receptor activity. So you look at the structure of dopamine, it is almost the same with our beta phenylethylamine, but there is no hydroxyl attachment on the beta carbon. Now with the hydroxyl substitution on beta carbon or beta to the amine group, and position 1 or carbon 1 to the aromatic ring. If there is hydroxyl substitution, that will greatly enhance agonist activity at both of our alpha and beta receptor. So that is a must. It largely decreases our CNS activity because it lowers lipid solubility. So if you can remember, our hydroxyl is very hydrophilic in nature or water loving. So if we have attachment of hydroxyl, that will lower lipid solubility and lower ability to permeate blood-brain barrier. So, for example, ephedrine and methamphetamine. So, our ephedrine is less lipophilic due to the presence of hydroxyl, so it has lesser CNS activity, while the methamphetamine is very potent because it has no hydroxyl in our carbon 1 or beta carbon, and it has alkyl substitution in carbon 2 or alpha carbon, which is more lipophilic, and therefore it can cross our blood-brain barrier easily. So now we've reached to the third chunk of our beta-phenyl ethylamine structure, and that is with our benzene ring and R3 substitution. So originally, our two hydroxy substituents are attached in position 3 and position 4. So the 3,4 dihydroxy substituted benzene ring is a must for excellent receptor activity for both of our alpha and beta sites. Now, if our positioning of hydroxyl will be changed, for example, it will become 3 and 5 position of our 2-hydroxy compounds, it will become more substrate or it will become a subject for degradation of our enzyme COMT. So if it will be degraded or targeted by COMT, then it will produce poor oral bioavailability. And poor oral bioavailability can affect our duration of action in the body. So, therefore, the attachment of hydroxyl and even the positioning of the hydroxyl in our aromatic compound in the benzene ring has an effect into the bioavailability of our drug aside from its selectivity with the receptors between alpha over the other receptor, beta receptor. So moving forward, as a recap, substitution on the aromatic ring will provide maximal activity if our hydroxyl is attached in 3 and 4. So it depends on the presence of hydroxyl in 3 and 4 position. Compounds without one or both phenolic hydroxyl substituents can be metabolized by our COMT, and that will affect the duration of action and the oral bioavailability. So for our drugs without hydroxyl groups, the loss of hydroxyl groups on the ring and on the beta hydroxy group on the side chain lead to compounds that act almost by causing norepinephrine from sympathetic nerve terminals. So they lose their direct sympathomimetic activity. Also, if we have no hydroxyl on the ring, we have more central activity because hydroxyl is hydrophilic, and when you remove or when you lose it, that becomes or that makes our compound more lipophilic. Therefore, it can cross the blood-brain barrier, making it have more activity in our central nervous system. So just for example, our amphetamine and methamphetamine. So they lose the hydroxyl groups. That is why they are agonists or they stimulates our nervous system, and they have more effect on the central nervous system because they have more lipophilic substituent and are unsubstituted aromatic ring. Now, as a summary, this structure here and this figure here presents to you all the things that have mentioned and elaborated, all the modifications that we can do in R1, R2, and R3, and the different effect it can provide to the function or to the pharmacokinetic and pharmacodynamic or the pharmacology of our drug itself. So I hope you can look for examples or browse some drug literatures and compare the drugs present in your work area so you can understand why it acts as alpha agonist, alpha 1 or alpha 2, beta 1 or beta 2 agonists, and how they become beta or alpha blockers. So that would be all. Thank you.